Ladies and gentlemen, good morning and welcome to the International Conference on Geological Engineering and Geosciences 2021, Big City Challenges on Geohazard and Georesources. We would like to inform all participants of the International Conference who have just logged in to don't forget register yourself and fill the forms if necessary. And the registration can be found, the link can be found at the dashboard or the website. Your Excellencies, distinguished guests, ladies and gentlemen of all participants, let us now start with the playing of the Indonesian National Anthem. All participants remain seated. Thank you. Ladies and gentlemen, this international conference is hosted by Geological Engineering Department Faculty of Engineering Universitas Gadjah Mada and allow us to extend our gratitude to our sponsor, PT J Resources, Pertamina Geothermal Energy, PT Agincourt Resources, PT Bukit Asam Tbk, BP Brau Limited, PT Geopatra Solusindo Energi Pratama, Exxon Mobil Cepu Limited, Kementerian Pariwisata dan Ekonomi Kreatif Republik Indonesia, PT Meko E&P Indonesia, Premier Oil Natuna CBV, and also sponsored by SKK Migas, Ikatan Ahli Geologi Indonesia (IAGI), Masyarakat Geologi Ekonomi Indonesia (MGEI), Lembaga Ilmu Pengetahuan Indonesia, Environmental System Research Institute or ESRI Indonesia, Dinas Pariwisata Provinsi Daerah Istimewa Yogyakarta, keluarga alumni Universitas Gadjah Mada, also known as Kagama, keluarga alumni Teknik Geologi Universitas Gadjah Mada, also known as Kageogama, and also our media partners, PT Duta Visual Nusantara TV 7, Trans 7, Suara Gama, SKM Bulang Sumur, Kleperon, Petroleum ID, and thank you all for the sponsor, for all your support, and we would like to extend our gratitude. Hopefully this 3 days event will run smoothly and we can continue our good cooperation for our next events. Ladies and gentlemen, welcome to Universitas Gadjah Mada and welcome to International Conference on Geological Engineering and Georesources 2021, Big City Challenges on Geohazard and Georesources. On this beautiful morning, please allow us to give an overview of the conference program. On the first day, we will have an opening and key remarks by several honorable invitees, followed by panel discussion. On the second day, we will assemble for the plenary session and group discussion, and also continued by lunch and talk by experts from geological engineering and georesources in the afternoon. And on the third day, we will also continue the conference with the group discussion and also closing. Ladies and gentlemen, without further ado, we would like to invite the Dean of Faculty of Engineering Universitas Gadjah Mada, Professor Insinyur Nizam, MSc, PhD, IPM ASEAN. The floor is yours, Bapak. Professor Nizam?
I'm sorry, Mbak Ica, the dean is Insinyur Muhammad Fasis Wildan.
Okay, I'm sorry, my mistake. But Professor Nizam, the floor is yours.
Okay, thank you, Mbak Ica. I'm sorry, I'm Wasis Wildan, Mbak Ica. Yeah. Okay, Honorable Head of the Department of Geological Engineering Universitas Gadjah Mada, Dr. Agung Setianto, Honorable invited speakers, Professor Dwi Korita Karnawati, Head of Indonesian Meteorological, Climatological and Geophysical Agency, Professor Koichiro Watanabe from Kyushu University, Professor Junji Kiyono from Kyoto University, Professor Thomas Ruth from RWTH Aachen University, and Professor Raymond Aerosmith from Arizona State University, and also all the participants of this conference. Very good morning and Assalamualaikum warahmatullahi wabarakatuh. First of all, on behalf of the Faculty of Engineering Universitas Gadjah Mada, I have a great pleasure in welcoming all of you to the International Conference on Geological Engineering and Geosciences. I hope you are in a good condition and health. Although we are still in the difficult situation due to pandemic COVID-19, I appreciate the conference committee hosted by the Department of Geological Engineering, Universitas Gadjah Mada. I also appreciate to all the participants for attending this conference from your home or your office because you are not able to come to Yogyakarta at the moment. However, I hope you can visit and enjoy Yogyakarta city sometime in the future. This conference aims to bring together researchers, academia, industrial professionals, policymakers, and students to share experience, knowledge, and research results in the field of geological engineering and geosciences. In addition, this conference also aims to address common issues of georesources sustainability, renewable energy sources, and climate change-related geohazard and disaster in the development of urban areas. As we know that those issues need an integrated approach and collaborative effort in building and enhancing resilient cities. I do believe that this conference will be very beneficial to all the participants in enhancing our capacity and capability, and also in expanding our network in regional and international level, especially in the field of geological engineering and geosciences. I also believe that this conference is not only a place for presentation and discussion about the topics, but also to strengthen collaboration. To conclude, I would like to express my sincere gratitude to the invited speakers, steering committee, organizing committee, sponsors, all participants, and everyone who have made this event a success. I wish you all have a productive discussion and sharing research experience during this conference. And finally, by saying Bismillahirrahmanirrahim, I officially open this international conference on geological engineering and geosciences 2021. Thank you.
Thank you, Insinyur Muhammad Wasis Wildan, MSc PhD. And let's now continue to our welcome remarks from the Head of Department, Dr. Eng Agung Setianto, ST MSc IPM. The floor is yours, Bapak.
Thank you, Ica. Good morning, ladies and gentlemen. The Honorable and Excellencies Insinyur Muhammad Wasis Wildan, as the Dean of Faculty of Engineering Gadjah Mada University, Widodo SPMSc PhD, as the Head of Publisher and Publication Board Gadjah Mada University, distinguished professors, scientific committee members, and all reviewers, and also all respected participants and presenters. First of all, let us pray and thanks into our God, Allah Subhanahu wa Ta'ala, who has been give us some mercies, blessing, so we can attend gather in this online event with a good condition and happiness situation. My name is Agung Setianto, Head of the Geological Engineering Department, Faculty of Engineering, Gadjah Mada University. It's such an honor for me to speak on behalf of the host by giving you a warm welcome to the International Conference on Geological Engineering and Geosciences. The main topic of this conference is Big City Challenges on Geohazard and Georesources. This conference is aimed to address a common issue of georesources, sustainability, renewable energy sources, geohazard, and disaster in the development of urban area. By inviting international researchers, academics, participants, policymakers, and related communities to discuss, to share, exchange their latest research, recent case, reviewers, advanced method, and experience progress associated with the field of geological engineering and georesources. This conference invited reputable researchers from all over the world, such as from Japan, from Germany, USA, France, Vietnam, Thailand, Myanmar, Malaysia, Laos, Nepal, UK, and Czech Republics, and our scientific committee and reviewers. As the call of a full paper was announced on 15 October 2020 up to 19 February 2021, this conference has attracted more than 75 papers and posters submitted to the ICGOES submission system. After review, the scientific committee has selected around 63 papers and posters from different countries such as Japan, Germany, Myanmar, France, and also from Indonesia to be presented on this conference. We thank you for our keynote speaker for providing their time to join us and share their experience, expertise, and knowledge. That is first Professor Jundi Kyono from Kyoto University, Japan, Professor Dwi Korita Karnawati from Indonesian Agency for Meteorology, Climatology, and Geophysica, Indonesia, Professor J. Raymond R. Smith from Arizona State University, USA, Professor Koichiro Watanabe from Kyushu University, Japan, and Professor Thomas Rude from RWTH Aachen University, Germany. Finally, we hope that all of you could join, enjoy, take the opportunity to have a fruitful discussion and knowledge sharing in this conference. Thank you very much.
Thank you, Dr. Agung. Now we proceed to the plenary. Here we have Professor Emeritus Toshiaki Hasenaka from Center for Water Cycle, Marine Environment and Disaster Management, Kumamoto University. Professor Toshiaki Hasenaka is coming from the Graduate School of Science and Technology. His PhD in geology from Department of Geology and Geophysics, University of California, Berkeley. He has done extensive research in volcanology, geochemistry, and petrology of volcanic rocks from Mexico, Japan, and Indonesia, and he has been doing fieldwork in 13 volcanoes from Central and East Java. Professor Toshiaki Hasenaka will join us to introduce our keynote speech, and will introduce us from Ibu Rita, and then Professor Rude, and so on. Professor Toshiaki Hasenaka, the floor is yours.
Okay, thank you very much. Can you see me? It is not. Can you see me? Can you see me?
Not yet, Professor.
Oh.
Can you turn your camera on?
Camera is on, I think. It's,
okay, we can't see you.
Okay. How about this?
Hey, hi. Ohayo gozaimasu, Sensei.
Hello.
So how's the weather in Japan?
Do you hear me?
Yes, clearly. So how's the weather in Japan, Sensei?
Okay, now. Oh, very good, very good. And we can see nice cherry blossoms as you can see in my photo. Yeah.
Yeah,
great.
Very
Thank you.
handsome.
Okay, okay. Do you see me now?
Yes.
Oh, great, great. Okay. It is my pleasure and honor to become the chair of this special panel discussion event. And I want to put the agenda here. I want to start this panel discussion like this. There are 3 keynote speakers, and after that we have 4 panelists. And I ask each of those to speak like a 4 keynote speeches. That's 20 minutes. For panelist speech, maybe a few minutes. And then after that, we'll start discussion. Do you hear me?
Yes, Sensei.
Okay, great, great. Okay, I'll continue. And then we'll start discussion. And the first, we focus on discussion on keynote speech 1. And then after that, we move on to keynote speech 2 and 3. And after all those, I'll ask audience to join question and answer time. So is that clear to everybody? I hope this will organize our panel discussion.
Yes, Sensei.
Okay, so I want to introduce the first keynote speaker, Professor, please go back. Oh, great. Yeah, Professor Dwi Korita Kaunawati. She is the head of Indonesian Meteorological, Climatological, and Geophysical Agency. And also, the professor in environmental geology and disaster mitigation, Gadjah Mada University. She took a PhD in earth science in Leeds University in 1993. She works for vice president of the International Consortium of Landslides since 2015. She also is the chair of the Intergovernmental Coordination Group for the Indian Ocean Tsunami Warning and Mitigation System. So she has a very interesting career. I look forward to hearing your talk. Professor Dwi Korita, please. Okay, I'll pass my mic to Professor Dwi Korita.
Professor Dwi Korita, are you with us? Ibu Rita? Maybe we can move on to Professor Junji Kiono, Sensei?
Okay, then the second keynote speaker. Are you ready, Professor Kiono? Oh, Kiono Sensei, yeah, you're ready. Okay, okay, I'll change the order. First keynote speaker is going to be Professor Junji Kiono.
Okay.
He is a professor in Graduate School of Engineering, Kyoto University, and he got Doctor of Engineering, Graduate School of Civil Engineering, Kyoto University in Japan, in the year of 1992. He works in the fields of research. His fields of research is earthquake engineering, civil engineering, disaster prevention engineering. Currently, he works on earthquake and lifetime engineering. His laboratory covers a broad field from the estimation of strong ground motion in the near-fault zone to the investigations of mechanism of structural damage, human injury, and organizational disruption. His research field is very interesting, especially we think about earthquake disasters. Professor Kiyono, please, I pass my camera to you. Are you ready?
Kiyono Sensei, the mic is yours.
It's my great honor to have a keynote speech with Professor Dukorita Karunawati and Professor Ramon Aaron Smith and Professor Koichiro Watanabe and Professor Thomas Rood. So I also express my sincere appreciation to all the staffs in Gajah Mada University who organized this international conference. So this is a video taken 10 years ago in Tohoku earthquake. So last week, the March 11th, that was the 10th anniversary of Tohoku earthquake. The magnitude was 9.0 and almost the same as 2004 Indonesian of Sumatra earthquake and tsunami. So in this earthquake, so we had a long period ground motion observed in especially the big city. So please look at the left-hand figures. The strong ground motion started from Tohoku Sendai and propagate to Tokyo and Nagoya and Osaka. So these cities have a very deep basin. So that is one of the cause of long period and long duration ground motion. So please look at the right-hand side. This is the different earthquake. So upper two is the observed acceleration at the basement. And bottom two is the observed acceleration at the 24th floor. So you can find the basement, the main S-wave shaking. After main S-wave shaking, there is not high amplitude, but at the top of the floor, 24th floor, you can find very long period and long duration ground motion. So this figure shows the natural periods of various structures. So you can find the high-rise building or super high-rise building or base isolation system their natural periods are long, about 1.0 second to 4 or 5 seconds. Of course, other large infrastructures like long span bridge and oil tank that has a longer period. So we have the very, very large shaking table in Hyogo Prefecture. So this is the experiment that they assume the long period ground motion in the high-rise building. You can find what happened in the high-rise or super high-rise building. And inside of the building, also you can find. So there is many furnitures, copy machine, desk. So this kind of phenomena would occur in the long period ground motion. So other floors, there's many furnitures, but by attacking the long period ground motion, because this is high-rise building, so this kind of phenomena occurs. So in Bangkok, large amplitude shaking of high-rise building occurred in 2016. That earthquake occurred in Myanmar. The distance from the Myanmar is about 1,000 kilometers, the very, very long. But, and in this earthquake, so many people inside of the high-rise building, they frightened and rushed outside. But if there is a long period early warning system, and they know the level of shaking in advance, they would settle and probably act calmly. So the final goal is to propose and install the early warning system specified for the long period ground motion. In Japan, we already have a prototype, but this study aims to use the existing limited attenuation equations in Thailand. So this is a research flow on constructing a long period early warning in Bangkok. At first, we have to collect data for deep basin model in Bangkok metropolitan area, the borehole data, a microtremor observation, earthquake observation, and etc., etc. And we try to make the three-dimensional basin model. So, other is the data collection for ground motion prediction equations, and like earthquake records or peak ground acceleration, peak ground velocity, absolute acceleration response or relative velocity response, and so on. And once we get this kind of data, and when the earthquake occurred in Thailand, we know the magnitude and location of the earthquake, and we can estimate the long period shaking level. In Bangkok, there are many high-rise buildings and super high-rise buildings, and we know their natural period. And compare with the shaking level and the building, the height or building stories, so we can have the earthquake warning for long period ground motion. This is a flow of the research. At first, so we model the Bangkok basin, it is said, the very deep basin. At first, we use the borehole data. But borehole data in Bangkok, maybe up to 20 meters or 30 meters. The most of the borehole data is up to several tens meters. But there is another borehole data to find the aquifer explosion. We use this aquifer exploration data because this borehole is very deep. So we collect 103 borehole, and the data contains the 18 layers. So, but this is the point of data. So we interpolate to make the 3D model. So this is very famous interpolation method, the clicking. The arbitrary point we can estimate by using the existing data, the linear combination of existing data. The lambda is the clicking weight, and we can estimate arbitrary point depth. That is a kind of interpolation. So, as I said, there is 17 layers data, and we interpolate. This at the bottom figures an example of layer PN and the last bottom layers. But the problem is we don't find the parameter of wave velocity. That is the problem. So we combine this borehole data with microtremor array observation. So the number is not so many, but we conducted the array observation 5 points. So my colleague is in Mahidol Universities and Chiang University, and with those researchers, we conducted the array observation at this 4 university and 1 meteorological department. The array is from 3 meters to the radius of 3 meters to about 300 meters. And we conducted the array observation. This is a small array. Equipment is 4. And this small array is the velocity meters. And other large radius observation is done by this independent accelerometers. So we use the 5 accelerometers. And once we conduct this kind of array observation, we get the dispersion curve, the upper right, the dispersion curve of radio wave. So to fit this observed radio wave, we model the layer model with shear wave velocity or density or thickness and P wave velocity. So after getting the observation and we process to make this dispersion curve, and to fit observed dispersion curve, we make the model. We made the model. So this is after fitting the observed dispersion curve and the theoretical dispersion curve. So both is in good agreement. And after doing this, we estimate the shear wave velocity in each layer and layer model like this. We combine this model and the previous aquifer exploration model. And now this is ongoing. Not the exact one, but this is preliminary result of each layer. For example, the shear wave velocity is 100 meters per second, and this is 800 meters per second, and the bottom basin is like this. The deepest point is about 1.5 kilometer to 2.5. So next is the ground motion prediction equation. So this graph shows the new intensity scale based on absolute velocity response spectra. So upper figure shows the human behavior on the indoor of the high-rise building. Left is the absolute velocity, and right is absolute acceleration. The full black is impossible for standing, and half black is difficulty in standing, and quarter black is difficulty in walking. The vertical axis is the absolute velocity, this figure, and the right figure is absolute acceleration level. And horizontal is the period of the shaking. From this figure, you can find the indoor behavior due to the absolute velocity can be classified more clearly than acceleration here. So this means the absolute velocity is the better index compared with the acceleration. But why absolute velocity, not relative velocity? So this is a schematic diagram of shaking. Please look at the right-hand figures. So if this pendulum is the tall building, please image the high-rise building, the longer period. Maybe it's a natural period, it's 3 seconds, 4 seconds, 5 seconds. And if the long period ground motion attack, the shaking is like this. So the relative velocity is 0. You compare the ground and the pendulum. So the relative velocity is 0. But absolute velocity has large amplitude. So that's why we focus on the long period ground motion, and we wanted to know the behavior of the tall building. So the absolute velocity response is the good index. So there are not enough earthquake data in Thailand. So firstly, we make an attenuation equation by using Japanese data, like this equation. Once we give the magnitude and epicentral or hypocentral distance, so we can estimate the absolute velocity response. So the data is the 5 earthquakes observed in Japan, and the observation point is about 900. The magnitude range is from 5 to 7.3. And obtained a regression coefficient for long period, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So now we image the 40-story building. That natural period is 3 seconds. And we assume the magnitude 6.8 earthquake occurred. So the line is blue line. And we consider, now this is just an example. The epicentral distance, we can find 20 kilometers. So we estimate the absolute velocity response is 20 centimeters per second. So this means once the meteorological agency announces the magnitude and the location of the earthquake, so we can get the magnitude and epicentral distance, and we can estimate how is the absolute velocity. And please look at the right-hand side. So if we classify, so the bottom is difficult to walk from 15 to 50, or difficult to stand 50 to 100, more 100 centimeters per sec, impossible to stand. And in this case, so the difficult to walk. So by using this, so that people can recognize the earthquake level in advance and can take suitable countermeasures and to take a calm action. Okay, this is the conclusion. Long period ground motion strongly affect to mega cities. in which the high-rise, super high-rise, the base isolation building and large-scale infrastructures are constructed. So Bangkok is one of the mega cities. So we select this is the pilot city. And toward the final goal on the construction of long period early warning system in Bangkok, we have to make, at first we have to know the sedimentary basin characteristics. And although this is a preliminary model, so we made the deep basin model. And also long period ground motion prediction equations, regression analysis of absolute velocity response proposed by considering the case that enough data or equations are not prepared. As I said, there is no such kind of equation in Bangkok, so this time we apply the equation developed in Japan and just directly applied, but we have to consider that kind of situation. And by using this kind of equation, just after getting the information, magnitude and epicentral distance or hypocentral distance, early warning system can, earthquake early warning can issue for safety response. Okay, thank you for your kind attention. Thank you very much.
Okay, thank you very much, Professor Kiyono. Okay, everybody, do you hear me? The mic is back to me, I suppose. And we'll move the question and answer time later, as I introduced in the beginning. So I'm going to introduce the second speaker today. Actually, I already introduced Professor Ibu Rita, Dwi Korita Karnawati. Okay. I think I'll repeat. Yeah, she is the head of Indonesian Meteorological, Climatological, and Geophysical Agency, and she is a professor in environmental geology and disaster mitigation at Gajah Mada University. She took her PhD in Earth Science at Leeds University in 1993. Oh, okay. No, any problem?
Okay, fine.
Please continue, Sensei.
Okay, okay. If everything is okay, I'll continue. She also is the vice president of the International Consortium of Landslides since 2015. She's the chair of the Intergovernmental Coordination Group of the Indian Ocean Tsunami Warning and Mitigation System. Seems like she does a lot of work, and I'm interested to hear her talk. Professor Dwi Korita, please. I'll pass my mic to you.
Well, thank you very much, Professor Harsaneka, for a very keen introduction. And good morning, ladies and gentlemen, dear colleagues, professors, special to Professor Junji Kiyono. Thanks so much for very enlightening presentation earlier. I learned very much from what you just presented. And thank you for that. And also thanks to the head of department. Sorry, also thanks to the dean of the Faculty of Engineering, the head of the department, and colleagues all in Geological Engineering department. First of all, I would like to highlight the earthquake and tsunami mitigation in Yogyakarta International Airport. As we know, the Indian Ocean coastline was quite challenging due to the vulnerability of the region. So that's why our agency, together with universities, especially with ITB and Gajah Mada University, work together in order to provide and to prepare the mitigation for the safety of the international airport. Next slide, please. Well, in terms of tectonic setting, the airport, this map, you can see to the subduction zone of Indian Ocean. We can see the subduction zone border exactly in the south of the airport to about 200 kilometers distance from the airport. And the subduction zone, actually the mega subduction zone, because it's extended starting from Aceh, the west part of Aceh, from the Indian Ocean situated in the west part of Aceh, go down to South Sumatra, and then continues turn right to Java Island up to Nusa Tenggara Island. So this subduction zone is really mega zone, and it consists of several segments of faults. And one of the segments, actually two of the segments, exactly in the front of the airport. And the worst scenario, this segment of subduction zone can reactivate it or can release the energy due to the earthquake, potential earthquake with a magnitude of 8.7. So that the worst scenario that we have to mitigate it, the earthquake with the magnitude of 8.7. So we work together with the university to handle or to mitigate that potential megatrust earthquake. Next slide, please. Well, I believe everyone has understood how the tsunami occurred due to the subduction, and now we don't, in the record, this moment, this minute, no earthquake occurred yet, because the slip is in the locking condition. It has been in the locking condition for many years, more than 10 years, even perhaps 100 years more. So that's why the accumulation of rock stress fields is still ongoing. Until then, the rock stress fields pass the limit of the elasticity, then that will result in the sudden fault, which occurs as a strong earthquake or megatrust earthquake. And this trigger the tsunami. So we predict potential or the worst scenario of the highest level tsunami inundation, which can hit the airport. Next, I would like to explain more how we try to deal with that potential worst scenario. Next, please. Just for your illustration, again, Yogyakarta International Airport, we can see there, and the data from 2008 up to 2009 period in Java and its surrounding areas, we can see the red dots. The red dots are the epicenter of the earthquake, and clearly we can see there is the zone where there is no red dots yet. So that is believed to be the gap zone, which have hidden accumulation of stress field stress, which can release anytime, especially in the worst scenario with the magnitude of the earthquake 8.7, which can induce the tsunami. Next slide, please. Well, actually, there have been series of earthquakes with the magnitude around 7 up to 7.9. We can see in that, we can see how the Yogyakarta National Airport situated exactly face to face with that earthquake zone. Next slide, please. Next slide. Yes. This also the evidence of tsunami in southern Java can be found in the BMKG Indonesian tsunami catalog, where the tsunami have occurred, including in 1840, induced by the earthquake magnitude 7.5, up to July 17, 2006, tsunami induced by the earthquake magnitude 7.7. Next slide, please. So basically, all those figures showing how vulnerable is the airport due to megatrust earthquake with potential tsunami. So please allow me to jump into slide number, hang on a minute, slide number 12, please. Slide number 12. Yeah. And there was a study from LIPI and ITB indicating that paleo tsunami exists there, especially in Kulon Progo. And based on paleo tsunami deposit in Kulon Progo, it was identified tsunami age is about 1800 before present. And BMKG as well as ITB Paleo Tsunami Research Team since 2010 have also found tsunami deposits in Pangandaran Beach, West Java and Cilacap. They are considered to have originated from past tsunami. So it means the pattern of the tsunami is real to the airport. Next. Well, here we can see the area in red is the indicated area with high potential for large earthquake in the south of Java Island. The zone may break apart with a magnitude of 8.7, or if both together, for the worst scenario is the magnitude of 9.1. This according to Professor Sri Widiantoro just last year. So we call that as a study. Next, all those patterns of the earthquake, megatrust earthquake and tsunami, we are scientists together with the Badan Meteorologi Geophysics work together how to protect or how to mitigate the international airport from the threat of tsunami. And this airport has been launched last year in August by the President of Republic Indonesia, and together with the launching of Indonesian tsunami warning system, which incorporated in the airport. So this is the first airport, perhaps in in ASEAN or in Indonesia, has been supported by a really tsunami warning system. Next slide, please. Now, I'd like to introduce how the tsunami warning system set up in Indonesia, and then later on how the setup in Yogyakarta International Airport. Indonesia's tsunami early warning system operates now more than 370 seismic sensors and more than 18,000 tsunami model scenarios from the earthquake sources throughout Indonesia. Actually, the system was developed in 2008, so now it has been 13 years, and now we are in the process of redeveloping by integrating sea bottom sensors. So we learn from Japan, also from United States, to prepare for the INACBT or Indonesian cable-based tsunami method. The goal of Indonesian tsunami warning system is detecting the earthquake events in a timely manner and provides tsunami early warning to responsible institutions and officials in order to have appropriate response from the community to reduce and minimize the impact of disaster. This system is actually designed only or limited only for the tectonic tsunami. It cannot detect the non-tectonic tsunami. So this was developed due to Banda Aceh megatrust earthquake and tsunami. So that's why when we have non-tectonic tsunami, like the tsunami in in Sunda Straits, due to the volcanic eruption, the system could not detect those tsunami because it was not induced by the earthquake. Another thing, when we have Palu tsunami, actually this system detected the tsunami in Palu because the tsunami was induced by earthquake-induced landslide. So directly induced by the landslide, and landslide was induced by the earthquake. Unfortunately, the time required to designate, to launch the warning system was 5 minutes. And in Japan, they have minutes to provide the time for launching the tsunami in 3 minutes. So this system was 2 minutes late than Japan, because actually in 2018, the technology, highest technology for warning system we learned that was in Japan. And the technology in Japan in 2018 was, sorry, I repeat it again, the technology of Indonesia for tsunami in 2018 was equal to the technology of Japan for tsunami warning system in 1988. So we were 20 years late for the tsunami warning system compared to Japan in 2018. So that's why we work hard, we try to learn from Japan, from United States, from Australia, how to improve the innovation of this early warning system. And finally, in 2019, by the end of 2019 or early 2020, we just finished Japan. We can provide early warning system in 3 minutes. After we tried very hard, we improved the sensors, the numbers of sensors, we improved the modeling, and finally, we now manage as well, like what Japan has achieved, providing the tsunami warning in 3 minutes after the hit of earthquake. So thanks to Japan that we can learn from those best practices. And next, please. Oh, hang on a minute, sorry. Please, a few slides. So basically, our system comprises 3 components. That the monitoring systems by using the Internet of Things, which was installed in 2008. Again, we learn from Japan and from other countries, by using Internet of Things. Then the processing system, which is supported by the artificial intelligence. It can calculate automatically without human to find to get the value of magnitude, the position of the earthquake, and the depth of the epicenter, as well as the possibility of the tsunami. So the warning system of the tsunami never used buoy. It has been very successful global hoax that Indonesia tsunami warning system using buoy, and the buoy was stolen, so that Indonesia could not provide warning system because the buoy was stolen. I really concerned with that global hoax, and at this opportunity I would like to tell the truth. Basically, Indonesian tsunami warning system never used buoy up to now, because we implement mathematical modeling, implement Internet of Things and artificial intelligence with the big data for calculating by mathematical model, calculating the prediction of tsunami, not the buoy record. We never record the sea level from the buoy in order to give the warning. So the warning provided by mathematical calculation to predict potential tsunami. So it can be correct when we predict the tsunami. Tsunami have not yet occurred, and the predict the tsunami may or will occur in 30 minutes. So 30 minutes later, tsunami can occur or may not occur. So when we use early, the terms of early, the prediction must be before the occurrence of the tsunami. So when we mention so for instance, the earthquake occurred at 9 p.m. So the prediction of tsunami can be at 9:40. So there is about 30 or 40 minutes golden time to prepare for the next 40 minutes tsunami. That means the early warning system, which is implemented in Indonesia and I believe also in Japan. However, if we use buoy, we give early warning, actually not early warning, we will give late warning when tsunami hit the buoy. When tsunami hit the buoy, so the buoy can take the record that tsunami has hit the buoy. Then the warning will disseminate or launch. It means the warning given when the tsunami has occurred. That will be too late, because the distance of buoy to Indonesian coastline is quite close. So only 5 minutes left, 10 minutes left, or maybe less than 10 minutes. So that means that becomes late warning system. So this is the reason why Indonesia never used buoy for the warning system. Well, then after processing, we deliver the warning through the dissemination system, which is located in each BPBD or local disaster agency, local disaster management agency, which must be open 24 hours. Unfortunately, this is the truth. Tsunami always open after the office hour, and we have no authority to make the local agency to be open 24 hours. So like in Palu, the local agency has closed and tsunami occurred. So that's why the warning, which must be launched by the local agency by pressing the button, because the button for launching tsunami is in the local agency. So there was no button, there was no warning provided because the local agency has closed. So this is the weakness of this program, because BMKG has no authority to make the local agency to be open 24 hours. So learning from that case, BMKG together with the ministers or related ministers and institutions that need to prepare the presidential decree for Indonesian tsunami warning system, which just launched the end of 2019. So by using presidential decree, it means president has instructed to all local agency to be ready 24 hours to receive the warning from BMKG, then to disseminate to the people. Earlier, in order to avoid the bottleneck of the information in the local agency due to the closed office, BMKG since 2017 has managed to disseminate the warning, not only depend on the local agency. So our warning can be disseminated directly through mobile application or through social media, radio, television. So despite of the close of the local agency office, the warning still can be spread to the community directly to his hand in their mobile phone. So next, please. This is the end-to-end system for tsunami early warning. Actually, consists of upstream part and downstream part. The upstream part, in this part we have sensors, that the earthquake sensors or seismograph connected with the IoT and satellite communication. These sensors directly recorded the signals of the earthquake that transmitted automatically instantly to the artificial intelligence or supercomputer in BMKG headquarters. Then we can immediately notice or alert with the earthquake event, especially the magnitude, the position, and the potential of tsunami occurrence. That's through the thousands of modeling potential of tsunami prediction. Then the results of the calculation or processing immediately transferred to downstream. Those interface institutions which is responsible to disseminate, to spread the information from BMKG through the society. So actually there is interface institutions with responsible to be ready for 24 hours, like what BMKG conducted, to immediately disseminate to the society. Those institutions are BNPB, local government, media, army, and police. Apart from that, due to some problems sometimes in the interface institution, we provide the mobile applications, social media, YouTube, in order to back up the dissemination of the information. Next slide, please. So, to monitor the earthquake activity, we have hundreds of sensors, and now still some development to add more sensors, especially at the bottom of the ocean. Because by using the sensor at the bottom of the ocean, it has a accelerometer as well as hydrostatic pressure. So from the hydrostatic pressure, we can also give indication of any tsunami, which may also induce by non-tectonic tsunami. So this is the way how we solve the problem, how to tackle the non-tectonic tsunami, by placing hydrostatic pressure at the bottom of the ocean, so we can detect as early as possible the change of hydrostatic pressure due to any kind of tsunami. Next slide, please. So I think, yes, this is the equipment of Indonesian tsunami warning system in Yogyakarta International Airport. We have installed intensity meter to measure the level or intensity of the earthquake shaking and the level of damage caused by the earthquake. We also set up the earthquake early warning system, instrument for earthquake early warning system, but this is still under development, not yet ready for the earthquake early warning system. Then later on it will be provided through the application in the mobile phone. But the intensity meter and accelerometer has been installed and in operation, ready in operation. And finally, we also provide warning receiving system generation. We can receive any information about earthquake and tsunami within 2 up to 4 minutes after the earthquake occurs. Next slide, please. Then, before we develop the airport, we conducted a microzonation at international airport in order to support the design of the airport. The design of the airport is prepared for the megathrust earthquake 8.7, 8.8 megathrust earthquake. Next. And also, BMKG has conducted mapping to detect the thickness of the sediment underneath the airport for supporting the design based on the ground motion synthetic. So this airport has been designed to be resistant, resistant for the earthquake of 8.7, and actually the airport is prepared for the terminal. So the height of the airport has been calculated that the mezzanine level and the second level for the shelter for tsunami. So if there is a tsunami occur in surrounding airport, everyone, the guests, the people are requested to go up to the mezzanine level and to the second level. Next, please. So this is the tsunami hazard map in Yogyakarta International Airport. So actually the ground level and the first level is prepared to be hit by tsunami. And due to the existence of the tsunami, due to the existence of the airport, so the tsunami can be retained, not goes beyond the highway. So actually the highway can be safe. Without the airport, the highway can be inundated by tsunami, but by having airport, the inundation can be reduced because retained by the airport. And also the airport supporting the community for having the shelter. The shelter or the airport itself can occupy for about 10,000 people in the terminal, in the level mezzanine and level 2, and then there is spatial shelter provided beyond the airport. It can occupied by at least 2,000 people at the same time. Next slide, please. So, Yogyakarta must have an evacuation plan. So the plan is for vertical and horizontal evacuation plan, and then strong multi-story structure at the airport for evacuation. Yes, it has been designed for that. And then install evacuation signs and provide an assembly point, as well as the ability of the warning receiver system and display for earthquake information and tsunami early warning at the airport. Set up some local tsunami sirens, please. So this is the SOP which is provided when the earthquake occurs. It has been disseminated to airport authorities as well as to the people today we are in the airport, nearby airport, to conduct sekolah lapang gempa dan tsunami. We conduct a community education surrounding the airport for preparing tsunami readiness, and hopefully this can help society to be more. This is the evacuation route which is provided, as I mentioned before. How the people must be directed to go up to the mezzanine level and to the second level. That's the people in the airport and surrounding. For the people outside the airport or in the yard of the airport, it is directed to evacuate into the crisis center, which can be occupied for 2,000 people. So this is the tsunami evacuation crisis center area outside the building on the left, and evacuation drill is in preparation now. All right, and next slide, please. Next. So the completeness of tsunami warning system combines 72 sensors installed airport and ground control go, those investigator, accelerometer, warning system, warning receiver system, new generation. We just install radar tsunami, but it is still under development. We work together with the Minister of Communication Japan. Now we still ongoing in preparation, and then we provide Icgeos, and BPPT will provide buoy. This buoy is not for warning system. Type and buoy, that's for verification, not for warning system. But to verify, check whether the tsunami is really coming from a recorder of the gates and buoy. And also, we have communication network for information and tsunami warning. It is connected to the global network because when there is tsunami, we must disseminate that to all other airports in Indonesia and in the world. And then we have operational room, also tsunami early warning sirens at the terminals, towers, runways, crisis center, and airport courtyards. And of course, there is an evacuation route, then also a gathering point and evacuation guide team. Next. That's all from me, and thank you very much for your kind attention. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Okay, thank you very much, Professor Dwi Korita. That was a very interesting talk. And on behalf of organizing committee, we apologize that we changed the turn of your talk. We haven't waited until the second talk. Sorry about that. Okay, let's move on to the last keynote speech, which will be provided by Professor Ramon Arrowsmith. Professor Ramon Smith is the professor of Arizona State University School of Earth and Space Exploration, and he got his PhD, Geological and Environmental Sciences, Stanford University in 1995. More than 25 years experience. He has more than 25 years experience studying the earthquake geology, paleoseismology, and geomorphology of fault zones, and publishing about their history of activity and hazards. He is a co-founder and co-PI of the Open Topography Effort, a portal to the largest collection of freely available high-resolution topography data. Well, thank you for waiting, Professor Ramon Arrowsmith. I'm going to pass my mic to you, please.
Okay, thank you very much for this opportunity. Let me share my screen and get my presentation ready. Okay, I want to start off by thanking you, Hasenaka Sensei, for guiding us during this session, and also terima kasih to my fellow keynote speakers. I'm learning very much, and I appreciate the opportunity to be part of this conversation. And also thank you to the leadership and faculty of UGM and the department. And also thank you to the staff for the very hard work to organize such an important and well-run meeting. So today I want to speak about sharpening our view of active faults with a couple of examples that may be relevant for the discussion. So what is right in front of us, and where many of you are, is you are very evidently experiencing the challenge of geohazards for big cities as we look at the active fault map of Java, and this is recently published by Marliani et al. In Tectonics, and compare that with the map below that shows the population density of Java. And this is just one example, but this is a major one where we see the challenge of the fact that more and more people are living closer and closer to dangerous faults. And so as much as we can do to improve our understanding of this system, the more we can help each other. So today, my outline, I will give I'll talk about three things, each one briefly. The first one is about community scale earthquake forecasting that's being done in California. The second one is some recent results on topographic differencing. And the final one is machine learning that we've applied for object detection for active surface processes. And so hopefully these may be interesting and give us some good discussion later. So just comparing Java to California, the plate boundary here is actually onshore, and this map also shows the big city challenges for California, where Los Angeles is here in this red polygon and San Francisco is here in this big red polygon. The population is not as dense or as large as Java, but still it is a large population and also a lot of business and infrastructure. And so this is crossed by active faults, including the San Andreas fault, which is shown here in orange. And this is a simple part of the San Andreas system where we see the black dots show plate tectonic motion of 320 kilometers in the last 24 million years along this system. We can also see at the 1,000 to 10,000 year time scale that this deformation is localized to a narrow zone in this part of the system with more than 34 millimeters per year measured by this offset stream channel. And then at decadal timescales, so just the last 10 years, we can see the accumulation of strain across the system. So these are dots, these are GPS velocity measurements in this rectangle crossing the San Andreas Fault here, and this is the north 40 west velocity, so this direction, and we see that there's a gradient right on top of the San Andreas Fault, and this is consistent with deep buried slip of 37 to 30 millimeters per year. So we have this case of steady strain accumulation and release along this part of the south central San Andreas Fault. So it's a relatively simple part of the system, but we will see that the challenge is difficult even here for forecasting behavior. So when we talk about earthquake forecasting, there are a number of ingredients. And the first is we need to have fault models that specify the spatial geometry of the major active faults. Then we need to have a deformation model to load the system that can come from fault slip rates, but also geodetic models and other measures to provide the input deformation budget. And then the earthquake rate models are ones that we assume the behavior, the frequency, and magnitude distribution for earthquakes recurring within the system and their rates as a function of the deformation model or budget. And then we have to report the results in a probabilistic sense so that it can be useful in a forecast. And so this work is being done in California, and it's one of the good global examples of a earthquake forecast model with discrete fault system idealized. And the main work is, there's actually three components. There's a time-independent model, a time-dependent model, and an ETOS model. The time-independent model is the long-term rate of expected earthquakes. And you can see in this map, we see the major fault system of the plate boundary in California is broken into many small segments. They're actually 7 kilometer long by 14 or more tall, or down the dip. And they're color-coded in this case by the participation rate per year of larger than magnitude 6.7 earthquakes. So in other words, these reddest ones, or the purple ones, are 10 to the minus 2, which means a 100-year average recurrence for those faults, for these large earthquakes. Now this then is the reference model, and the time-dependent example in the upper left shows the probability gains relative to the time-independent model given the historical record and recent paleoseismology. So it shows in red that unfortunately it looks like the San Andreas Fault is a little bit overdue for another big earthquake, and then other parts of the system may be a little bit slower in terms of their likely failure. And then the more advanced example is the ETOS, or epidemic type aftershock sequence, which is a computation of the probability gain for earthquakes that involve additional faults within the system. So this is probability gain for a magnitude 7 on this part of the fault system, and we see that this is the classic example of earthquake forecasting the problem, which is we have high gain. We may gain by 100 or 1,000 times probability. However, we can see on the right side, 10 to the minus 2 per year is actually 10 to the minus 5 per day. So even though we go up by 10 to the 2, we're still at 10 to the minus 3. So it's still a difficult forecast to make because the probability is still low in spite of the high gain. So that's the first part of my presentation, is to talk a little bit about earthquake forecasting, and then the next 2 parts of the talk I'll discuss some work along the creeping section right here of the San Andreas Fault, and then I'll end with some of our work in the Eastern California shear zone. So this work on the creeping section of the San Andreas Fault uses an examination of the aseismic deformation as a laboratory to examine the active deformation along the fault zone. And this work is led by Chelsea Scott, who is a research scientist who works with me in my research group, and Steve DeLong, who is a US Geological Survey scientist. And this was recently published in the Geophysical Research Letters. And so you can see in the picture here, we're looking right along the San Andreas Fault at a sag pond. And this area is the zone of high creep, more than 30 millimeters per year. So we can measure creep rates, and you can see just the example on the right. The fault goes through some urban environments, and it breaks the infrastructure. In this case, it's the side of the road, but you can see more of the road is deforming. And so we can measure fault creep rates across the San Andreas system to assess the amount of moment accumulation relative to what's released by creep. And we want to constrain this aseismic creep along the central San Andreas Fault and Calaveras faults by differencing repeat LiDAR topography. And then we constrain this very deep, very densely, every 400 meters. And what we can show is that portions of the central San Andreas Fault creep at more than 30 millimeters per year, meaning it's almost the same as the long-term plate rate, as I showed at the beginning. And at a few locations, we can start to examine the local geomorphology compared against the deformation zone measured by the differenced topography. So here we are in central California along the San Andreas Fault, and this part of the San Andreas Fault is very interesting, and it's unusual because it is dominated by aseismic creep. And what that means is that even though there are many earthquakes, they're very small, and the most of the moment release is by aseismic slippage along the fault zone. And this zone is bound by the 1906 earthquake zone to the northwest and the 1857 earthquake zone to the southeast. So two locked parts of the system breaking with magnitude 7.8 or larger earthquakes. But between them is this zone of creep, which is highly localized. It's also the oldest part of the San Andreas Fault. And so we wanted to examine what is happening here. And we can also assess a technical challenge, which is how to do this topographic differencing now that we have airborne laser scanning that's more than 10 years old. So we can take old scans and compare them against new ones. And we've been using a methodology called topographic differencing, but we do iterative closest point. And it's been developed for robotic navigation and other engineering applications in these examples below. But then Nissen et al. And Scott et al. Have published papers recently applying this, especially to as part of our collaboration with our Japanese colleagues. And you can see on the left, this is the east-northeast, north-northwest, and the vertical components of the displacement field from the Kumamoto earthquake. So we did the same activity where we take the before and after airborne laser scans. So the plane flies over the fault zone, measuring the ground by ranging of the laser beam, and has high accuracy. These points are within a few centimeters of global reference frame. And so then we compute the 3D rigid body deformation that will align the 2 point clouds in each 50 or so meter window. And we can also look at uncertainty by looking at the divergence of the different windows next to each other and assume that that divergence is associated with error. Of course, it's except when it crosses the fault, but we know where the fault is, we think. So this work was done, what we're doing is taking this 2007 and 2005 laser scans along the San Andreas Fault with 2 points per square meter density and comparing them against 2018 laser scans with 4 to 9 points per square meter. And this represents a significant investment in data collection and then the patience to wait so we could measure change. And so we had some challenges. You see the laser scans are aligned along the fault zone, but there's some difficulties like vegetation changes, so we only used ground points. Landslides, like this one here on the left, you can see in the hillshade, cause a lot of displacement perpendicular to the fault zone, so down in this case on this image. And there were also some flight line errors that caused problems in the vertical, but also in the northeast direction, which is luckily perpendicular to the fault trace. And so the biggest signal we expect is northwest, and that has a good error. And so here's what we can do. We can compute the difference between the before and after measurements, and so we get a fault parallel displacement is shown in color here in meters. So you see negative 0.3 to plus 0.7, and you see the discontinuity, which is where the fault is. And so from this, then we can compute a creep, which is the displacement discontinuity across that fault zone. So the displacement on the southwest side minus the northeast side, that vector, and that gives us the creep rate, or the creep, and then we divide by the time, by 11 or 13 years to get the rate. And so this is the result, which I'm really impressed by. I think this is really exciting because, yes, hello? Oh, okay. You can see the, it's 0 to 150 kilometers of measurements along the fault zone every 400 meters. And you see the map of that northwest displacement rate below along the fault zone. And then above we see the creep rate with the right lateral measurement, so parallel to the fault in blue. And then red is the perpendicular, so the shortening or opening of the fault zone. And black is the vertical. And we know that the red and the vertical have a little bit more of an error due to the flight line problems, but the blue measurements, which are the most important ones, are not suffering that problem. So as we go from the southeast, we can see this rapid increase in creep rate as we go from this locked section to the southeast into the Parkfield section of the San Andreas Fault, which has some magnitude 6 events on average every 20 to 40 years. And then we go into the main creep zone, and we see a very rich behavior of fluctuation of the rate. And then what's interesting, as we come to the northwest, the San Andreas bifurcates into the main San Andreas and the Calaveras Fault. And the green shows the Calaveras right lateral measurements. And you can see that they plus the blue would fill this gap here. So there's a kind of equal partitioning between the two fault surfaces as we move to the north. So it's really very rich data set and much more to do to interpret these data, I think. We can see also then that there's a difference in the aperture. And so you can see that with different measures across the fault zone, so the differencing is the one I'm showing here, which is about 1 to 2 kilometers. There are some measurements that are across a narrower zone and then some that are across a wider zone. And so when we compare them, we can see that those that are across a wider zone, like these geodolite and EDM measurements, give larger measurements of creep than the topographic differencing. And those with narrower apertures give a lower creep measurement. And that's quite interesting and maybe explainable that it shows that there's a little bit greater slip at depth or more distributed deformation, and that is measured only by the larger aperture. And so we can see here the application to a piece of the fault zone that's just a few kilometers long, and you see the mapping above these two different versions of the map, but it has the main fault trace on one side of the shear zone with secondary structures between. So any of these secondary faults seems to be well manifest by the geomorphology. However, what we can see in the creep is that only a small portion of the system is activated, and we can see which faults remain active at this decadal timescale. So this, for me, becomes quite interesting because we can compare different timescales of deformation of along the shear zone. So it's very interesting, and so there's many opportunities going forward. We want to study the strain accumulation and see if there are places along the fault zone where maybe there's still some locked zones and we might expect larger earthquakes in the future. We want to study the active traces, as I've just showed, in the last slide. And then the last 2 points are to use this to understand fault displacement hazard more carefully, and also the mechanical properties of the fault zone, what controls the distribution of deformation. So I have just a few minutes, but I'll go now. Let's go to Eastern California to see some additional recent work. And so this one is a problem of bedrock fault scarps. And we don't understand them very well. They're more complicated than simple fault scarps in alluvial material. And so what we've done is to look at a zone of bedrock fault scarps that are formed in a 760,000-year-old ignimbrite. This is an area called the Bishop Tuff, or the volcanic tablelands, and there are many beautiful normal fault scarps in this system. And what we have done is we have a hypothesis that the fracturing is due to 3 different processes: volcanic cooling, tectonic fracturing due to the faulting, and geomorphic fracturing due to collisions and thermal processes. And these processes all together produce the particles on the fault scarp face. And so what we wanted to do was start to measure them by measuring traits, which means properties like the area of the rocks, their eccentricity, so are they more round or more elongate, and what is the orientation of the long axis. And so I've been working on this with one of my colleagues, Janeshwar Das, who's a robotics expert, and our colleagues and students. And we start off with imaging using a UAV, this small drone, compute the digital elevation model and orthophotography, and use deep learning to make a semantic map, a map of rocks. And then we can do geomorphology with that. So here's what we use. We use a deep neural network architecture called mask region CNN, convolutional neural network. And so we do the training to identify some of the rocks and train the system. And then we use different combinations of the imagery, RGB plus the elevation as another channel. And we put these together and we can output the results, which is the maps of the particles. So at first you may say, oh, this seems kind of boring, who cares about rocks? But to me it's really exciting because we can see already the grain size distribution. So now we see the rocks are color-coded by their sizes or their areas, and we can map many of them. This is 500 meters. And this example, we were able to map 12,000 particles. And so here they are along this fault scarp. And every 4 meters, I made a bin. And so we can look at how many particles per bin, gives us kind of a particle density. But also we can measure the size of the particles. And we can convert the area to the phi, which is the equivalent diameter in millimeters. It's a commonly used sedimentary measure of grain size. And what we can see then in each of these bins, we can compute the median grain size. So in this case, the median grain size is close to minus 8.8, which is about the size of an American football. It's also similar to a soccer football as well. But it shows you that the grain size is actually fairly large. But we also can start to examine, well, where are the largest particles and where's the largest variation in the particles sizes, so the shape of the histogram of grain size. And we can see that they're near the steps in the fault trace, which means we're accessing the original volcanic columns, which haven't been broken more by tectonic faulting or geomorphic processes. So this to me is quite exciting because we can start to look at relative rates of motion along these faults and look at the geomorphic response to that deformation, but then also use the properties of the sedimentary characteristics of these rock traits along the fault zone to maybe estimate relative rates of activity. And this is still two-dimensional, it's map-based, so our next step is to go to full 3D and start mapping the objects in 3 dimensions and move into fragile geologic features and precariously balanced rocks applications. So thank you very much. Terima kasih. We thank you very much. I'm very grateful to my colleagues in UGM, and my wife and I visited last in 2019, and thank you again for the hospitality and the opportunity to present today.
Okay, thank you very much, Professor Ramon Arrowsmith. It was very interesting talk, especially it deals with not only San Andres fault, you mentioned about Kumamoto earthquake and also Indonesian cases. Okay, we move on to, say, group session. We are supposed to get together, right? Please, I ask the controller to move on to the group session. Okay. So we get together and take pictures, right? Thank you very much for this chance. Great, great. Okay, we are together, all of us, all the speakers and panelists. All right, thank you very much. Okay, terima kasih. Can I move on? Okay, great. All right, I want to make a short summary because the title of panel discussion today is the role of academic in building resilient cities. And I understand all three keynote speakers made a great contribution to building resilient cities from their own researches. And I was very much impressed. And now I'm going to move to the next session, which is introduction of three panelists, or 3 and 1, maybe, including me, 4 panelists. And then after the introduction of panelists and short talk by panelists, we move on to the discussion time. The first panelist is Professor Subagio Pramumijoyo. He is a professor of geological engineering, University, Gajah Mada University, and he got doctor from Paris University, France, 1991. And his area of research is tectonic earthquake geology and structural geology. He has more than 25 years experience studying earthquake geology and active fault kinematics in Indonesia. And he has geological principal investigator in Sulawesi and Papua expeditions. And Professor Subagio, please, I pass the camera and mic to you.
Okay, thank you very much, Professor Hasanaka. Can you hear me? Hello?
Yes, Pak Bagio, we can hear you.
Okay, thank you. Thank you, Professor Hasanaka and Professor Arrowsmith and Professor Kiporita. You know that this talk example of university study is really expressed by Professor Kiono talk and Professor Arrowsmith talk this morning. And Professor Rita have told about the dissemination to the people, especially surrounding Yogyakarta International Airport. And I think the most important to here is to have resilient people. For the people their interest is for the result of the scientific research in the university. What is the result? I mean, what is the warning itself? So we in studying geohazard, you know, there is some several time recurrence. For example, for an earthquake, very long time, and then for volcanic, it's more. There is some very long recurrence. For example, from Merapi and close to, from Yogyakarta, it is around 7 to 10 years time recurrence. And then for the landslide, I think it is more frequent volcanic earthquake. So the most important here is how to educate the people to know the symptom of the geohazard. We have an example in Indonesia, for example, in Nias Island. The people know the word of smoke. Smoke is local language. That it is a warning. If there is an earthquake, however, there will be a tsunami accompanied or not, the people should be running to the hillside to climb up the hills automatically. Yeah, it is educated by their ancestor by storytelling, I think. But in Indonesia, I think there is not what is communication between grassroots and the decision maker. Sometimes it's very long distance like this. So, for example, Burita have told about the stolen buoy. It means that the people don't understand what is the meaning of buoy for the self-sovereign of the others peoples. Yeah. For the moment, I think I said like this. Maybe for the next comment from other panelists. Thank you, Professor Hasinaka.
Okay, thank you, Professor Subagio. Thank you for your short talk. And we move on to the second panelist, Dr. Agun Halijoko. He's the head of Center of Disaster Studies in University Gadjah Mada. And he's associate professor in geological engineering, geological engineering department, University Gadjah Mada. and he got his doctorate degree in economic geology from Graduate School of Engineering, Kyushu University in 2004. He has extensive research in volcanic systems in Java, Sumatra, Molucca, Sulawesi, and Flores, Indonesia. Dr. Agung Halijoko, please, I'm going to pass my mic to you.
Okay, good morning. Thank you very much, Professor Hasenaka, for introduction. So let me share the screen first. Right. Okay, thank you very much for the committee that gave me a chance to talk in this occasion. Yeah, we have learned from another speaker like Professor Vikorita, Professor Aru Schmidt, and also Professor Kiono, related mostly in the earthquake. Also Professor Subagio Pramanijoyo, related to local wisdom in Indonesia. So I would like to talk about our research activity on volcanology. Sorry, no, not this one. So I would like to talk about our research and education activity on volcanology in UGM. Why we have important things to do with the volcano, especially volcanology in Indonesia. So this picture shows the distribution, global distribution of Holocene volcanoes. And we can see here that Indonesia, we have a lot of active volcano. And when we plot with the number of population within the radius about 30 kilometers from the volcano, so we will have a closer view here. So we can see that actually Indonesian people are exposed to the volcanic risk, especially in Jawa, because here you can see that the color symbol here indicate the number of population within the radius 30 kilometers, and in Jawa the color is red. It's mean it's more than 1 million people live in the area within 30 kilometer radius. So it's way that volcanology is important for us, especially to construct the cities resilient. So one of the factor is to understand the risk or understand the geology of the area. So in case of Indonesia, so we have a volcanic chain from the northern tip of Sumatra through the Java until the Nusa Tenggara or Flores Island, then continue in the north arm of Sulawesi and Halmahera Island. But due to the number of population in Java is more dense, so actually the people live in Java is facing volcanic hazard, exposed to the volcanic hazard. So our research on volcanology, especially right now, we focus on the eruption history of Bromo Tengger caldera, eruption history of volcano, because we have not only recently erupt volcanoes, but also we have a case that we have let's see, like a Sinabung area. So there was no eruption for a long time, more than around 1,000 years without an eruption. So, but then in 2010, the volcano was erupting, yeah. And the eruption is continue until now. And when we facing the Sinabung volcano, we don't have any knowledge about how the Sinabung volcano erupt or the behavior of Sinabung. So in Indonesia, we call it or we classify the volcano into A, B, or C. So the type A volcano means that the volcano has eruption since year 1,600. But B, it's said that the volcano is active, but we have no data about the eruption since year 1,600. So then the government, Indonesian government, have some monitoring or observation, volcano observation, but mainly for the type A volcano. But the type B volcano has no observation office. So even the type B volcano may have eruption in the future or next the short future, but if we don't have any information about the behavior, so then we may have some difficulties during the mitigation when the volcano erupts. It's when that our research team right now is about the eruption history, and we have worked in some volcano like Bromo Tengger Caldera Complex, Slamet volcano, Ijen volcano, and also Iniria volcano. So today I would like to talk or give an introduction about the Bromo Tengger Caldera Complex. So this afternoon, our student will present about the remote sensing study on the Bromo Tengger Caldera. So Bromo Tengger Caldera is located in the East Java. So it like a nested caldera, and there are many post caldera volcanoes inside the caldera. This picture shows the image of Bromo Tengger Caldera. So we have a huge caldera here, yeah. And this back is Bromo Tengger Caldera complex. And actually, there is also older remnant of like a caldera, but we focus on the Bromo Tengger Caldera here. And from the previous research or report that at least there are 3 caldera or activities, forming eruption activities in this place. That is called Ngatisari, that is Ijo, and Lautan Pasir. And Lautan Pasir is the youngest caldera forming eruption, and the product is mostly scoria flow. And in this study, we were to know the eruption history and also the type of eruption in the past. And fortunately, there is the valley, the Sapiker Valley, that is deeply cut valley, dissected valley here. So we did some field work within the Sapi-Kerep Valley, we expect that we can find not only the youngest deposit, but also the older deposit. So from the fieldwork, we found that the youngest or the deposit that is related with the youngest caldera activities of Lautan Pasir is exposed in the northern part of the volcano. Yeah, so it's quite thick scoria flow. Yes, the scoria flow that overlay the very old deposit here. So this we believe that this is the youngest because this is just on the surface. Yeah, on the surface. So this deposit should be the youngest deposit, and due to the huge deposit, so this should be the result of caldera forming eruption. Another older deposit, probably it's from Ngatisari caldera forming deposit. Yeah, we found so in the location in the one of waterfall here, and this deposit is overlain by the lava, so lava deposit. So that is it means that yeah, this caldera forming deposit should be older than the other scoria flow that is product of Lautan Pasir. So we suspect or we interpret that this deposit is result of Ngatisari caldera forming eruption. So based on our study here, so we try to know about the age of eruption, and so the Lautan Pasir, the age is in line with the result of the previous study. It is about 30 kilo annum or 30,000 years ago, but we don't have any data about the Ngatisari caldera forming eruption because of there is no until now we cannot find any suitable sample for dating. Yeah, so this is just example of our result. So this is also the deposit of Lautan Pasir product, but it's closer to the source. So it's interlayer between scoria flow and pyroclastic fall deposit. And the important thing that we must continue the research in this volcano, that the volcano is not silicic magma or silicic magma volcano, but it's more mafic. So because in the common sense that the caldera forming eruption should be resulted from the silicic magma, but in Bromo, we can see that even it's more, it can caldera forming eruption. I think this will give contribution to our knowledge about the volcanology in Indonesia. And for volcanology, so we have a master program in the Department of Geological Engineering, and we have a double degree program with the Kyushu University, and this is one of students who joined in the our double degree program with Kyushu University, and then we do studies in the Ijen volcano to understand the eruption type of Ijen volcano, post-caldera volcanoes. And then for community service, so we have like a consultation for the East Java province government for the mining of sulfur at Icgeos volcano. Also, we have a joint study with the BPPT-KG office or Merapi Observation Office in Yogyakarta. I think that's all my talk, Professor Hasinaka. Thank you for the.
Oh, okay. Thank you very much, Professor Agun Halijoko-san. In contrast to other speakers today who are specialized in earthquakes and tsunami, Dr. Agun Halijoko is one of the leading scientists who study volcanoes. So I look forward to the discussion with him after all the speeches. Okay, next speaker. Next speaker is Professor Faisal Fathani. He's a director of Gamma Ina Tech, Universitas Gadjah Mada. He's a professor in civil engineering at Gadjah Mada University. He got his PhD in geotechnical engineering, Tokyo University of Agriculture and Technology in 2005. He's a vice president of International Consortium on Geodisaster Reduction. Well, he has many jobs. I'm surprised. And he is a deputy director of Multimodal Sediment Disaster Network. He is also a director of Center for Disaster Mitigation and Technological Innovation. He's a director of Director Magister for Disaster Management, Graduate School of Universitas Gadjah Mada. His field of expertise covers landslide monitoring and early warning system, numerical modeling of landslide movement, sediment-related disaster mitigation. He patented 5 landslide detection monitoring systems, and he's a project leader in the international standard on early warning system. Okay, Professor Faisal Fathani, please, I pass my mic to you.
So thank you very much, Professor Hasinaka, and also all participants of this conference. First, I would like to express our gratitude for the committee of this conference, and also for the exceptional and interesting presentation from all of the keynote speakers. So I would like to highlight the theme of this panel discussion is the role of academics in building resilient cities. So as we know that all of the countries in the world, when we develop the national development plan, we need to refer to the SDGs, yeah, Sustainable Development Goals. So among 17 goals, so goals number 11 is sustainable cities and communities. So that is very in line with the theme of our discussion today. So disaster risk management cuts across different aspects and sectors. So 10 among 17 SDGs or 17th goal is closely related with disaster risk management. So that we need to establish the role of disaster risk management, disaster risk reductions as a core development strategy. So in order to do that, for us in this forum, all of the academia, we need to promote and integrate disaster risk management into sustainable development and investment decision making. So we need to invest something in order to achieve what has been discussed by Professor Rita. As we know, BMKG works very hard for having a good information for earthquake and also early warning for tsunami. And also from Professor Tiono and also Professor Aerosmith, that how we do a good research related to earthquake disaster. Here I wrote 5 points of the role of academia related to our team today in building resilient cities. The first one is need to keep doing an integrated research, starting from basic research and of course up to the most adaptive and applicable one. So this is very cross-related what have been explained by Professor Subagio Pramowijoyo, my teacher, how to put science into practices. And the second one, we need to promote based on our long experience in research and also our research maps, we need to promote a standard or guideline, national level or international level, in order to support the governments, private sectors, and community in dealing with disasters. In this case, Gadjah Mada University, in cooperation with Indonesian Meteorological Climatological Agency, we work together in promote international standard for landslide early warning systems, and then tsunami early warning systems, flood, and also volcanic eruptions. Just in 2019, we published the ISO 22328/1 multi-disasters early warning systems by International Standard Organization in Geneva. And then also for national level, we have a lot of work in working with the standard, starting for the mapping, landslide mapping, for example, early warning system for landslide and any other disasters. And then the third one is how to direct the regulation and policy. This is very important because now in Indonesia we have the presidential decree from 2019 for earthquake information and tsunami early warning systems. And now we work also to establish the presidential decree for multimodal disaster early warning systems. And then the fourth one is to support central and local governments to develop action plan, contingency plan, and also for arranging the budget or budgeting in building resilient cities. We need to answer the gap because we have so many research, so many publication, but why that disasters still cause many casualties or many victims for disaster. So we need to work hard in order to bridge and also to support the central and local government in working in disaster risk management. And the last one, number 5, is how to conduct training, public education, like student community services, like Dr. Agung Harijoko has explained. So this also our main challenge that the academician, the academia like us, our final mission is how to create the future leader in working with for disaster risk management in all over the world. So I think that's all my point, and very sorry that I'm still in the hospital just 5 minutes before I get the first vaccination for me for COVID-19. So thank you very much, Professor Hasanaka. I give back to you.
Okay, thank you very much, Professor Faisal Faisal. You just came back from hospital. Wow, I'm surprised to hear that.
No, I'm still in the hospital now. Yeah,
oh
for 30-minute observation after the vaccination. Okay, thank you.
Oh my God. Okay, thank you for joining us. And lastly, I'm going to give my talk about well, as a panelist. And could you put my slides? The controller. Okay, yeah. I'm going to talk about the lessons from Kumamoto earthquake 2016. And because we're running short, I'm going to make this very short time. Okay. The next slide, please. This shows area of small earthquake, big and aftershocks, and all small earthquakes in red, which is on the right side. And the location of, say, municipal units, Kumamoto City, Kashima Town, and Mashiki Town is the place which received the big shocks, big ground movement. Another place, Nishihara village, that experienced one big ground motion. And along Futagawa Fault, the Futagawa Fault is slightly red. And damage at the bottom, as of August 10, 2017, 15 deaths, and this connected with earthquake, it's 194. And number of serious or slight injuries to more than 2,700. Totally destroyed houses are more than 8,000, seriously damaged house more than 34,000, and partially damaged house more than 150,000, including mine. Okay, go on to next slide. Yeah, these are the photos. Well, crashed house in Mashiki town, which experienced strong ground motion twice. There are two big earthquakes, and then right is a huge landslide at Aso Caldera area, that is a volcanic area east of main town, Kumamoto city area. And the bottom left is the office of our director, CWMD director, and the right. Well, what happened after the earthquake? So there are many, say, garbages, broken household materials, and that was a lot of, say, problems after the earthquakes. And then, oh, yeah, please. Okay, and next slide, yeah. And one of the problems I have to point out is many people said we did not expect earthquake because we believed Kumamoto is a safe place. And on the contrary, scientists said, yeah, we warned that there are active faults passing through Kumamoto and surrounding cities, and there are such information in websites. So why this happened? Seems like there are not enough communication between local residents and scientists. Everybody thought that the large earthquake of April 14 was a main shock. That was another problem. The main big, much larger earthquakes occurred to April 16, 2 days after that. And there's one thing I was impressed is a firefighter's story. Firefighters in Nishihara village were very quick and successful in rescuing people and their collapsed houses. And why that happened was they were making daily evacuation drills. Daily rescue drills are very important. That's the point of this. Everybody or some people knew there is an active fault, but they are not really prepared in mind or in activity. But those people are making daily drills. That's the big difference. And also, what we learned is the daily communication between scientists and residents are very important. The next slide, please. The topic today is, say, academic role in making resilient cities. So let's think about the university tasks. Our task, especially we are in a local university, that's research, education, and social contributions. And after the earthquakes, after such event, academics spend more time in social activities. That's becoming more important. And exchanging workforce between academics and local government, or some people actually belong to a local government but are working in the university, or other people who are in the private companies doing civil engineering work but who are put into academics. Those exchanges are very important. That's what I found out. Also, communication working together, those people in time of crisis is very important for making things work. The bottom left is Mashiki Lab that our Kumamoto University made in Mashiki town for the daily communication between local residents and the university. The right one is a drill made by students. We are making training course for students to prepare for disasters. Next slide, please. Next, please. Maybe this is the end. Okay, yeah. The bottom one, Bosaishi, yeah, the bottom one, Bosaishi, that's a Japanese word. It means qualified people with knowledge and skills for disasters. There are more than 100,000 of Bosaishi, or qualified people in Japan. We have regular training course, which was provided in university or which was provided in local cities, and that really works. Okay, and our task, probably academic task, is preservation of disaster remains. That works for warning for future disasters. And also we do guided tours to show disaster areas. That's another important thing, to show people how disaster occur and what's dangerous. Okay, that's the end of my say talk, and we move on to question and answer and discussion time. Please close my slides. First, well, we don't have enough time, but let's talk about a keynote speech, the first, which is provided by Professor Kiyono. And any questions or any comments from other speakers or panelists, please raise hands or maybe put your question in chat. Well, Kiyono-san stressed the movement at very high level building is very dangerous in case of earthquakes, and also he studied a lot. He put a lot of effort in studying ground structures of Bangkok, Thailand, and studied the groundwater level. In connection with the ground movement of in terms of earthquakes. And any questions for that? I want to focus on academic roles in making resilient cities. That's the title of this panel discussion. How about the person who is doing similar work? Okay, please, Ramon-san.
Yes, I wanted to ask Professor Kiyono about the experimental facility. This is very expensive to have such a facility, but obviously is so important. And so does he see that there will be more of the experimentation? Is this difficult for academics to ask access to the system? And do you also do some computer simulation as part of the physical experimentation? Thank you.
Thank you very much. So, as you know, this experiment was done in the E-Defense, called E-Defense, so located in Hyogo Prefecture, near Kobe. And many experiments have done up to now. And one of the experiments is a high-rise building and a super high-rise building. But that is a full-scale test. And as you said, it takes huge amount of money to do. So the researcher collaborated with some big companies and to get the budget from the government and so on. So you said, so the computer simulation is very important, and I agree with you. But before that, so we have to know the fundamental phenomena or fundamental parameters of, from the experiment. So I think that is the first stage to do the experiment. And after that, the computer simulation and to complete the research. So, but in a year, about 3 or 4 big experiments, not only the building, but also the large soil box, and inside of the soil box there is a pipeline or other human behavior to put not the actual person, but the dummy dolls put on the shaking table and take the measurement. So many kind of experiment has done, and I think that is to get the basic parameters and to obtain the basic phenomena. And after that, the computer simulation will be done.
Okay, thank you very much. Is that enough, Professor?
Yes, that was excellent. Excellent. Thank you. It was useful to learn some more.
And I want to have some comments from Professor Subagio, who is doing similar work. What do you think? Any comments, Professor Subagio? Please turn on the mic. Please turn on the mic.
Still mute, Pak Bagio.
I have open.
Good,
Yes.
good. Okay, I can hear you.
What the comment to the presentation of Professor Kiono?
Yes.
Okay. It's very excellent. I think it is the task of the academician. Yeah? I think just like what have Professor Kiono done. And then from the experiment, we can do more to the practice, and then so the result is transferred to the people to understand what it means the result of the research. And I think there is a question of Mr. Pipat for Professor Kiono about next, what next? What the experiment, your experiment to the Bangkok people. It is the most important, I think.
Yes. So thank you very much, Professor Subagio. So I remember, so I went to Sulawesi Island, Palu, with you to do the observation, microtremor observation. I remember. So as you said, to make clear the fundamental phenomena and to transfer the knowledge to the community is very important. But for example, so that kind of large-scale experiment, so that was not done by myself, other researchers, but that was on the home page, and we can get that kind of video freely. So that is very important. So what can I say? The awareness of the community and dissemination of the result of our knowledge and our experiment to the community is very important. So we have to emphasize that kind of behavior to increase the awareness of the public and disseminate the result to the public. Okay, thank you very much.
Other comment or questions?
Mr. Basanta?
Okay.
Basanta. And Arif Ismanto.
Hi, Basanta from Nepal.
Okay.
It's a wonderful presentation, as Professor Kiono also mentioned, and Professor Fatani also working on this area. And UGM has a very good understanding about dissemination of scientific knowledge that produced in academia. to the community. So, for example, in Nepal, we have been talking in in academia, we produce really good results, but there's a long, huge gap between the academics and the community that we need to apply these things. So, how do you apply this kind of, scientific technologies to the Indonesian part, to the communities? So maybe Professor Fatani can, illustrate on that a bit more. Thank you.
So the question goes to Professor Faisal Fatani, Mr. Basanta?
Yes, please.
So, Pak Faisal, the mic is still off, Pak.
Yeah, thank you very much. Yeah, Basandra, we met several times,
Yeah.
Previously, yeah. Yeah, that's the main challenge for the researcher like us, because we try to, we have the scientific community with high level of scientific requirement, but also we should work with the community. In this case, I work with Professor Yogyakarta Karnawati since 2000s, and we developed some kind like community hazard maps. So the map is that simple, so that the community could understand and could follow the direction for evacuation, for example. So that's one example, for example, for the map. And other things that we try to use the strategic program for disaster risk reduction, starting from providing information and good assessment on the local conditions. So it means if we work for the flood disasters or landslide disasters, so we need to understand clearly about the risk assessment on that area. The second one is to provide the countermeasures and also early warning systems. This technology is working in this part, the second part. Yeah. For countermeasures, because I come from civil engineering department, so we design a lot of like landslide prevention, sabu dam, sabu bridge in all over Indonesia, and also we also work for early warning systems, referring or complying with the ISO standard and also Indonesian standard. In this case, we apply the landslide, flood, and debris flow early warning system at 33 provinces in Indonesia and more than 120 cities or regencies, and also in Myanmar, in other countries. Yeah? And the third level is the public education, socialization, and discussion with the community. The third one and the last one, that's our goal, is to achieve community resilience. So we have 4 steps in order to provide strategic programs to put science into practice. So that's my answer. Thank you.
Thank you.
Thank you. Thank you, Professor Faisal. And the next question is coming from Arif Ismanto. The mic is yours. You can ask directly to our speakers today.
Thank you. Good morning, gentlemen. First, my apologies. I use video off because the link in my position is not good.
It's okay, but can you turn the volume? Can turn up the volume? We cannot hear you.
Okay. Wait a second.
Yeah, it's okay.
Okay, how about now? It's okay.
Louder.
保存点が非常に面白いという、どういうふうにしてますかっていう質問が、
Okay,
チャットで出てる、答えなきゃいけないね。
Okay. Can you hear me clearly?
Not really. Can you add more volume first, please?
Yeah.
It's too small.
Okay, how about now?
Better. Now better. Okay. Please, your question?
Yeah, my first question is go to Professor Junji Kiono. Professor Kiono has provided a good result of the study of the basin model using the seismic for the aquifer model. My question is, do you have a study or comparison with the method that you apply
Sorry, I could not catch the comparison of.
Shallow level.
Mr. Arif, we are losing you. Can you repeat the question, please?
Probably using, but basically that's a very regression linear using data, Japan with the other data for that seismic 3D model. Sorry, and then my next question is for Professor.
We are losing you. Maybe you can, instead of can type at the chat box, because we cannot hear your voice.
Is, how do you think about the? Okay.
I'm so sorry. Yeah, we are losing you. So the next question is coming from Samantha Clark.
I will type it.
Okay. Amanda, okay. Miss Amanda, are you here with us?
Yes, I'm here.
Okay. Your question, please.
Okay, I typed it in the chat, but I was interested to hear about the strategy in Japan of preserving the damage and then giving tours to the public of the damage. And so I was wondering if they have worked out the best way to use past damage for public education. And I also wanted to know if this was a common practice outside of Japan, if other countries were doing this.
And your question goes to Professor Hasenaka, Professor Kiono? Or
Hasenaka.
Hasenaka-sensei. Okay.
Yes.
Hasenaka-sensei, please. The mic, Sensei. Okay. No. Okay.
All right. Oh, okay. Can you hear me? Thank you very much for your question. Yeah. We think preservation of a disaster site is very important, and we do the same project in after Kumamoto earthquake. But it is like a struggle between scientists and what shall I say, local government or construction workers, because the idea for government, local government and construction workers is put everything back into back state. That means erase all the damages. But some of us really like keeping earthquake cracks or deficit, the displacement of earthquakes or damaged houses is very important to show what happens in the case of natural disasters. So, well, it is not really easy. We try to preserve those damaged things, but there are many people against that. Especially, you think about that. If you lose your very important persons in a house or in an area, then you really want to erase your memory in that district. So sometimes we really have to think about the feeling of those people living there. So we are trying to do best, but it's a really struggle between scientists or those workers and local residents or government or construction workers. Please understand that. But we are successful in some of the areas. Is that enough?
Yes, thank you very much.
Okay, thank you. Let's move on to Ms. Najma Aurora. Can you turn on your mic?
Good morning, good night, good afternoon to everyone, the speaker. My name is Najma Aurora. I am a freshman in Gajah Mada University, and I would like to ask, I have two questions. The first one is directed to Mr. Raymond Arrowsmith. I'm very curious regarding your recent study. You color-coded boulders based on their size, and I haven't really grasped why, like how does it, how will it affect your data and the data that you're studying? Thank you. And my second question is directed into all of the professors in Indonesia. I want to know why it is kind of very difficult for us. I mean, based on the recent articles that I've been reading, it's very difficult for us to apply early warning system in Indonesia. And why is it that? Why does that happen? Thank you so much.
So, Professor Raymond?
Yes, thank you very much for this great question. So we use the same method. The machine learning that we use is the same method that's been developed for identifying objects in pictures, like on the internet. They, you know, maybe you say, well, how do we find pictures of cats on the internet? It's the same technology. So it uses deep learning to separate the objects. It's called semantic mapping of just the pixels into higher level meaning. So instead of the cats or something else, we're looking just for the rocks. And it's very simple in the end, but it gives us these traits or properties of each rock. And you can imagine how long it would take you to map 12,000 rocks. It would take many, many days. But using this approach, we can do it in just 20 or 30 minutes in the computer. But then the idea is that these simple traits reflect the underlying processes, like how the fault scarp is growing, and maybe that reflects the underlying rate of earthquakes or fault slip rate. So I hope I've answered your question, but thank you for it.
Okay, next question goes to all the professors in Indonesia from Ms. Najma. Why is it difficult to apply early warning system in our country? Maybe one of you or two of you can help us answer the question. Professor Subagio?
To Professor Faisal Fatani, I think.
Okay, Professor Fatani, please.
Okay, thank you very much. As we know that early warning system is not only the equipment or the sensors. It consists of 4 quadrants. The first one is risk analysis or risk assessment. So we need to do a good analysis of the risk, not only technical aspect, but also for institutional aspect and also socio-economical aspect. That's the first one. And the second one is socialization and dissemination. All of the information, we need to communicate with the community, with the local authority, with all stakeholders in order to design or define what we are going to do. That is the second one. The third one is early warnings and also warning systems and also warning criteria. So that's the technical part. And the last one, which is we put less attention, is the response capability. It means that if the siren rang, what should we do? Should we evacuate now? Should we bring the motorcycle? Should we bring the refrigerator with us, with the livestock, the coast, or everything? So that's in the ISO standard and also national standard of early warning systems. We define it as 5 different parameters. So that's the 4th one, and the last one is the commitment. Commitment from the local government or local community in order to operate and maintain the systems. Sorry, Professor from Japan, Professor Hasenaka and also Professor Kiyono, Professor Aerosmith. There is a different approach from the developed countries and also the developing countries. In developing countries, we need to make sure that all of the equipment we install in the field, we have somebody to commit to maintain and operate the systems. Otherwise, it will be stolen or it will not functioning. So that's also the big challenge. Why that Miss Atma just now asked the Indonesian professor. So it's still a big challenge, but we work on that direction. Not only installing the technical things, but also we combine the hybrid socio and technical approach in order to establish a good early warning systems. Thank you very much.
Thank you, Professor Faisal. Maybe Dr. Agung Harijoko, would you like to add something, Doctor?
Okay. In case of volcano disaster, that actually the early warning system is the monitoring system that is conducted by the Badan Geologi in Indonesia. So with the more monitoring, geophysics monitoring, geochemical monitoring, and then awareness. So and then the volcano can give recommendation to the local government when status of increase and they must evacuate the people. So it depends on the hazard type, yeah. But in the landslide, as explained by Professor Fatani, and but for the volcanic hazard, so the early warning system is actually the monitoring system that is already conducted in Indonesia. Thank you.
Thank you, all professors. Let's continue from the question from Mr. Arif to Kiono Sensei. Do you have any comparable study for your aquifer layer in basin model, probably with the magnetotelluric data, especially for shallower level? How is the result compared to seismic? Kiono Sensei, please. Do you have any comparable study for aquifer layer in basin model, Sensei?
So this time, so I firstly take into account the aquifer, because the aquifer exploration is maybe the hydrological research field. So I'm earthquake engineer, so deal with the aquifer data is for the first time. But so in the civil engineering field or earthquake engineering field, very shallow borehole is the widespread. So in Japan, more than several 10,000 borehole data is in the database. But most of the data is very, very shallow. In Bangkok, the same situation, the shallow data they have. So this time we use the aquifer data. But the problem is, as I said, there is no, for example, we need the soil data about the shear wave velocity or P wave velocity, density, and thickness, such kind of data. But the thickness and density is okay. But we don't have the shear wave velocity. That's the problem for the use of the data from the earthquake engineering field. So that's why we combine with the ambient vibration array observation. It becomes the answer for your question.
So hopefully it answer Mr. Ismanto's question. Mr. Ismanto's question is to Professor Ramon. May I extend? What is your advice for LIDAR characteristic in tropical areas where vegetation is thick? Will it impact the machine learning? Professor Raymond?
Yes, I answered this some already in the chat, but it is correct, and I'm sorry to give an example from the desert where we don't have a problem with vegetation. However, and so therefore some of the imaging will be difficult, but a high point count LiDAR is one of the best things to use for the dense vegetation environments. As we see in Japan, New Zealand, other places with more humid climates and dense vegetation, it's very effective at penetrating. So we may be limited to some degree to only the digital terrain models, but we can see under the vegetation, I think, many interesting things.
Okay, thank you, Professor Rahman. Are there any more questions from the audience or maybe between speakers and panelists today? Okay.
Yeah, I think okay.
Okay, Professor Subagio, yes?
Yeah. According to the question of Amanda, I have an experience visit the Awaji Island. There is a museum of earthquake. I think it is very nice view and conservation of the result of the earthquake. And I think the most important is the land that have faulted is offered by people. But for Indonesian people, for example, the fault is not so clear, and then the people is very dense. So to make free of the land is very expensive, and then the support of the government is not really clear, or so we have difficulties to practice to make a museum like in Awaji Island. For example, in the earthquake 2004, 2006 in Yogyakarta, for example. Yeah, we have a plan to make some museum, but we have constraint in the to have land for the museum. It is the difficulties. Our difficulties. Okay. Thank you.
Thank you much. Thank you.
Thank you, Professor Subagio. Are there any more questions? If not, then I'll return it to Hasenaka Sensei for summary. Hasenaka Sensei?
All right, can you hear me?
Yes.
Okay. Thank you very much, especially for the audience, people to join this discussion. I'm very much impressed. Everybody's curiosity about this problem. And we learned a lot from especially technological viewpoint of how much progress we have to make resilient cities, today's panel discussion topic. And of course, we have to think about countries with, say, more industrialized country, and the developing country makes big difference in approach. So the same approach shouldn't apply for like Thailand or Indonesia. That's something we have to think about. And each approach has its merit. So I hope Indonesian people, Gajah Mada people will make their own development of making resilient cities. I really hope this after this talk. Thank you very much for joining, everybody. I want to conclude and thank everybody, all the say keynote speakers, panelists, and audience. Thank you very much for joining today's panel discussion. Thank you very much.
Thank you.
Ladies and gentlemen, and that concludes the panel discussion today. We will have break time, and then we'll see you around 13:30 for parallelization. And you can have the Zoom link when you log in from the website. And then I am Icha. Thank you for today.
Thank you.
Thank you.
Terima kasih.
Indonesia lies in the convergence among three tectonic plates. This motherland is blessed with an amazing geological landscape, located along the string of volcanoes known as Ring of Fire, making Indonesia admired for its earth resources, yet anticipated for its geological disaster threats. Learning the characteristics of Indonesia's geological resources and hazards need to be supported with competent basic geological knowledge. Universitas Gadjah Mada Yogyakarta, through Department of Geological Engineering since its early establishment as an education and research media, study on structure, composition up to physical properties of this motherland, even the world. Established since August 1959, becoming part of Faculty of Engineering Universitas Gadjah Mada, Department of Geological Engineering has been one of the windows of education which contributes to create this country's best researchers and geologists. Carrying on the vision to become a leading center in applied geology, Geological Engineering UGM provides learnings, researches, and international qualification lecturers. Located in the complex of Faculty of Engineering Universitas Gadjah Mada, this campus is supported with comprehensive and modern education facilities, supported also with Geological Field Station in Bayat, Klaten. Delivers of dynamic teaching-learning interaction. Geological Engineering UGM, recognized for its continuous achievements, national and international. Every year, professional graduates are born. Geological Engineering UGM creates independent and creative researchers and geologists, professional who is able to cooperate and grow in global competition. The strengthening of sustainable network, quality recognition by national and international accreditation agencies, open the opportunities to cooperate with government institutions, private companies, renowned universities abroad, or even global workforce. Existing and potential cooperations open the opportunity to hold international graduate programs and to take part in double-degree programs at partners' institutions. This is the department that oversees quality and integrity. This is the learning space where professional graduates are born, graduates that bring the value of Pancasila. This is a place where independent, creative, and excellent human resources are born. This is Geological Engineering Department, Universitas Gadjah Mada dedicated to Indonesia.